Okay, so today we are going to talk about the last part of our rational functions, okay, and that is slant asymptotes. So when we were going through our rules and we were talking about our horizontal asymptotes, we had three rules. If the denominator is greater than the numerator, if the degree of the denominator is greater than the degree of the numerator, then you automatically have the line y equals 0. Okay, if they're equal, then we take the leading coefficients. The last type is when the numerator degree is greater than the denominator degree. Now, that doesn't produce a horizontal asymptote because it produces a slant asymptote. Okay. You might also see it referred to as an oblique asymptote. Okay, so again, this is when the degree of the numerator is greater than the degree of the denominator. The reason this happens, we'll see as we go along. So let's jump right into a problem. All right, so here, let's take a look at the function x squared minus x over x plus 1. So, did I graph it? Yes, I graphed it. All right, so here on the graph, all right, we can tell that there's a vertical asymptote, right? Because our graph is going up, and then all of a sudden it goes down, and then here it shoots down and then loops back up. But you can see there's not really, a horizontal asymptote that we're used to seeing. It looks like there's a big space that we're missing an area, right? So, but it's not a straight line like we saw before. You can kind of tell that we have a linear equation by looking at this part of the graph over here, this increasing part, and this increasing part over here, right? But what is this invisible boundary line that's stopping the graph from, flattening out? That's making it curve up like this, like such a sharp turn, right? So let's go through the steps that we did before, right? So we're going to find all the parts. So our y-intercept, we do the same. We plug in 0 for x, okay, and we get 0.00 because you get 0 in the numerator. Your x-intercept, you also get 0, 0, right? And we saw that. And we actually have a second x-intercept. I can't point to that because it's on the screen. Okay, so remember for the x-intercept, I lost. There we go. We just have to worry about the numerator. So we set the numerator, I don't know, I put parentheses equal to 0. Okay, here I can factor out an x. So I get my x equals 0, which we found, and I also get x equals 1. All right, so I have two x-intercepts. But again, this doesn't really help me. Our vertical asymptote, which we saw that we had, okay, x plus 1 equals 0 is at x equals -1. So going back to the graph, if I plot the line x equals -1, well, there we go. There is our sorry, I'm trying to learn this new program, and it's got some fancy stuff. Here we go. Cool. There we go. There's our asymptote. And let me make it, let's make it red. All right, so there's our vertical asymptote that, we know how to find. So this last part, Okay, because the numerator is a higher degree than the denominator, okay, we can simplify this. Remember, one of the things that we want to do is try to simplify this as far as possible to help us find all of our parts. So this way, because our numerator is a greater value than our denominator, we can use long division to simplify it. All right, so I'm going to set up our long division. I have x plus 1 on the outside. I have x squared minus x, and I'm going to put that plus 0 since we don't have a constant term. All right, so how do I get x to look like x squared? Well, I'm going to multiply it by x. I get x squared plus x. We subtract. This is negative 2x plus 0. How do I get an x to look like negative 2x? Well, I subtract by 2. Negative 2x minus 2. We subtract that. I have a remainder of 2. So I can rewrite my original function as x minus 2 plus 2 over x plus 1. Now here, whatever linear function that you end up with becomes your slant asymptote. Okay, so your slant asymptote is a linear equation. Okay, so we get the equation y equals x minus 2 is your slant asymptote. All right, now let's take a look at that on the graph now. So let's make a new line. Y equals x minus 2. And would you look at that? All right, I'll make this, we'll differentiate, that'll be blue, and I'll also make that dotted. All right, so there we can see we have this slanted line that bounds the equation. All right, so to graph it, if we needed to graph it, you have two options. You have your skinny parts, okay, and then you have your kind of larger parts. So we would do the same thing that we did before, right? I can use the fact that I know I have x-intercepts at 0 and 1. So that automatically tells me that I have one of the parts of the hyperbola here, okay, in this top skinny quadrant. So more than likely with these types of equations, the other part of your graph will be in the opposite side. Okay, so because it's in this top skinny part, I know I can automatically put my second part of the graph in the bottom skinny part. All right, if it was over here in the wider part, then your opposite part would go on the opposite wider part, right, on the right here, left and right. Okay, any questions about that? All right, let's do one more example. Okay. All right, so let's take a look at x squared minus x minus 2 over x minus 1. Okay, well, we can factor the numerator, so we can always do that to make sure nothing cancels out. We don't have any repeating removable discontinuities. So negative 2, we have 2 and 1. One of them has to be positive. One of them has to be negative. This is negative, so we're going to look like that. So even though these are similar, they're not the same sign, so we can't cancel anything out. but this does give us our x-intercepts. At -1 and 2. All right, so if we had to sketch this graph ourselves, I know I have an x-intercept at -1, and I have an x-intercept at 2. And my y-intercept, we plug in 0. I get -2 over -1 is +2. So somewhere up here at +2. All right, so again, this is, I don't have any lines drawn. This is just a rough sketch. It's not going to be perfect. Our vertical asymptote is always going to be the same. All right, your vertical asymptote, you're looking at your denominator. So we get the line x equals 1. So this is a good sign because we already have some points over on the left side and on the right side. Okay, so again, if you're just going through the normal situations, right, if we weren't just focusing on slant asymptotes, if I was looking for the horizontal asymptote, I would notice that n is greater than m. So that tells us that we have the slant. All right, when we have the slant, that means we divide. So when we divide, I'm going to go back and use this. I don't want to divide x minus 1 into these. That would be difficult. All right, so x minus 1 to get to look like x squared, we will multiply by x. So this cancels out, and this cancels out. So we're left with -2. So my slant asymptote is just the line y equals x. So that's going to go through the origin. Okay, with a slope of 1. So now, like we would do before, we would make sure we had some points. Well, here we have some points over here. So this one is going to come up like that. All right, we get close to the slant asymptote. We go through those points and we go up. And then that means that our other one is going to be over here. All right, and we're going to follow that wide kind of deal going on. All right, so we have this kind of wider situation than we did last time. We're not in the skinny part. Any questions about that? All right, so how do we feel about rational functions? Overall okay? Are we confused on some parts? You want me to go back? All right, so the last thing I want to talk to you about, I'll do it on this. So even though we haven't talked about this formally, can I get the whole thing in there? Okay, we've kind of referenced at this, but I want to focus on the domain real quick in these last few minutes that we got. So the domain of our rational functions is pretty much directly linked with our vertical asymptotes. So for most of these, they act like normal polynomials, right? Normal polynomials okay, our domain is all real numbers, okay? With rational functions, we have a few exceptions where our asymptotes are. So with our example before, I'll just pick the last one. Oh, x minus 1. Okay, you may be asked to find the domain. So again, to find the domain, we're really only worried about the bottom part, okay? Because the top part is going to be a normal polynomial, and all normal polynomials have a domain of all real numbers. So there's no restrictions up here, okay? It doesn't have to be greater than 0. There's nothing x can't equal in the numerator. But in the denominator, okay, we do have a restriction because we know that the denominator cannot equal 0. So to find the domain, okay, we would say for this, so we would say the domain is all real numbers except for x equals 1. All right, a less formal way of writing the domain, you could just say x can't equal 1. All right, but we really don't like this because it's not very definitive. All right, just saying x can't equal 1, that's not much. So if you did want to do it a little simpler than writing everything out, you could use function notation. I'm sorry, interval notation. All right, so this is saying all real numbers except for that 1. Okay, we skip over 1, and then we continue on. All right, so you may see that in the future where you're asked for the domain. So I just wanted to point that out. Okay, so tonight you're going to be doing a similar thing like you did Monday night, except you're going to have a slant asymptote instead of the horizontal asymptote. All right, and then we'll go over that tomorrow, and if you don't have any other questions, we're going to move on to exponential equations, something a little different. All right, guys, any issues, questions, concerns? How do we feel?